Alright guys, so today we're going to be jumping into how special relativity will help us explain Ampere's observations, namely that parallel currents will seem to attract each other and that anti-parallel currents seem to repel each other. And before we jump into this, I think we're going to have to nail down a slightly more specific understanding of what special relativity is. And if you might have heard the special relativity around as a word or a term, and you might be familiar with the general concept that time changes and the way in which time passes changes as you start going faster. And if you've seen the movie Interstellar, you might remember that Matthew McConaughey got on that crazy stupid fast spaceship, and as a result he only aged like a couple of years when everyone else aged much more, like I think like decades, maybe even a century. I don't know, it's been a little bit since I've seen that movie. But we can think of that phenomena that we noted in Interstellar as time dilation. And one of my beefs with time dilation is that while it tells you that time dilates, it doesn't exactly tell you where exactly such dilation is happening. So why don't we have that be the question that we're going to use to nail down our understanding of special relativity, at least to help us understand magnetism in a modern way as a relativistic phenomenon. So, where does time dilate? Well, why don't we start answering this question with the way that Einstein was thinking about it when he cooked up his idea of special relativity. And when he was cooking up the idea of special relativity, he was thinking about this thing that we call a light clock. And a light clock consists of two mirrors sandwiching a little beam of light, and it keeps time by the fact that it will take light a certain amount of time to leave this first mirror, bounce off the second one, and return to the first, and we'll call that amount of time T0. And now that we know that it takes that amount of time for this light to jump the gap, let's think about what happens when this clock starts moving, or at least when it looks like it starts moving to us. Well, when it looks like it starts moving, it looks like this light actually has to go to this second mirror, because this mirror isn't just staying here, it's actually over here. And then ditto for this mirror down here. So instead of just looking like it's going straight across and back, it actually has to take a more diagonal path to this mirror and then back down here, because it wants to get to this mirror at a certain time, which we now call t. And he used this Pythagorean triangle that you can find here to derive that this time that it originally took for light to bounce back in this super fast reference frame, T0, dilated by a factor of 1 over square root of 1 minus v over c quantity squared to yield you the new time t. And just so you know, this is called the Lorentz factor, gamma. That's not really going to come into play, but it's just a quick shorthand if you want to use it. But anyways, he held that this phenomena is not just true for some like little crazy light clock that he was thinking about. This phenomena had to be true for all other physical phenomena, because if this did not hold true for those phenomena, then we could end up having two different clocks that we trust equally as much. Like, let's say one depends on a certain very specific chemical reaction, the other depends on a very specific radioactive decay, and we could have two different clocks spitting us out two different times. As a result, we get two different velocities, two different accelerations, two different momentums, two different forces, two different energies. We get so many different things that we don't know what to make sense of. And the second that anything tries moving, the second that we have relative reference frames at all, that everything falls apart, all of our laws of physics fall apart, which by the fact that you and me are here today, we know is not the case, thank goodness. So we know that relativity will still preserve the laws of physics with time dilation, as long as time dilation occurs uniformly across all phenomena. And to cement this idea that the rate at which time passes is more slow in super fast moving reference frames, let me just direct you to a little example that I thought of on my own. It's not going to be, well, I don't know. I'll let you decide if it's as good as Einstein's, but this is just the way I like to think about it sometimes. So I'm going to have this wall, and I'm going to pin up a clock on it. And I'm going to get an identical clock, procure an identical clock. And then I'm just going to take this identical clock, because I took so much work in making them identical, I'm not going to mess with it as I slide it into my pocket. You're just going to have to trust me that they're still ticking the same, that they're still on sync. At the moment that I take that identical clock out of my pocket and now throw it at that clock on the wall. And when these two clocks hit each other, they're going to stop each other. And then I'm going to take these two clocks. I'm going to see how much time has passed. So in this one clock, it might look and register as if only about 1 second has passed, because it was moving so crazy stupid fast, like Matthew McConaughey. And because this other clock wasn't moving crazy stupid fast, like the people on Earth, it's going to register it as if more time has passed. So like, let's say this is 1 second, let's say this is 15 seconds. So that is how time dilation plays out in this scenario. But now, let's look at the two different reference frames that we have going on. So in the first one, we assign the relative motion of these two clocks to the clock that I threw out of my hand. But in this other one, from the point of view of the clock, we're going to assign the relative motion to this clock that was on the wall. In order to translate these reference frames, we know that we're just going to have to subtract this velocity, which will get us the same magnitude at work in both scenarios. And now, we have this velocity closing this gap in 15 seconds in this scenario, and we have this velocity closing this gap in 1 second in this other scenario. Which means that if we want our laws of physics to hold up in both of these reference frames, and if we want v times t to equal d, then that means that the length, when you go from this first reference frame to this other reference frame, must also contract by a factor of 1/15. Which means that not only do you have the time dilation t naught over 1 over square root of 1 minus v over c quantity squared equals t, but you also have the length contraction L naught times square root of 1 minus v over c quantity squared will get you L. And you notice that if you take this original length and divide it by the dilated time, that you will get the same velocity as you would if you take this contracted length and divide it by the non-dilated time. Which is why Matthew McConaughey, when aging slowly, also in fact actually became like svelter. This is sounding really good. If you guys have one of those machines, contact me. I really want one. But anyways, we're going to take these two phenomena of length contraction and time dilation, and we're going to use it to explain Ampere's observations and why we note magnetic phenomena, or how we understand them with our current knowledge of modern physics. And while we're on the realm of still thinking about things a little bit more abstractly, not thinking about wires that we can tangibly see or that I can tangibly set up demos for, we're going to think a little bit more about particles, just to start, because it's a little bit simpler. And we're going to think about two positively charged particles of equal charges. And because of Newton's second law, and because of Coulomb's law, we know that they're going to feel equal and opposite forces, and that the magnitude of that force is going to be k, q, q over r squared. And now, we're going to send them flying at that wall, and let's just say it's at the same speed that I sent that clock flying at the other clock. Which means that this force, we know, also implies an acceleration because of sigma f equals ma. And we know that as a result, that this acceleration, and we expect it to act over 15 seconds out in our lab frame. But in the reference frame of these charges, they only experience 1 second, they only experience that force for 1 second, and as a result, we don't see as much separation as we think we would in 15 seconds, we see the separation that we would expect for 1 second. So 15 seconds, but we only see 1 second. And we interpret this result as meaning that there must be less acceleration between these two particles, because that's how we see things. And as a result, we have less acceleration than can be explained by these forces, by these electrostatic forces, which means that we must have a second force at work accelerating these masses, and that force is an attractive force that keeps binding them together, and that is what we come to know as magnetism. And on a little side note, here you have two positive charges moving in the same direction. You could almost think about this as if it was current, and you see that two currents running parallel do indeed seem to attract. So the case looks pretty good for Ampere. Now, and why don't we just quickly consider what it would look like if these charges were opposite. So now that repulsive force is actually an attractive force. The attractive force does not get to act for as long as 15 seconds, but only 1, which means that you're not going to see as much closure between the two as you would expect, which means that there must be another repulsive force at work, which is again magnetism. And this time you have currents running in opposite directions. Alright, so why don't we move into wires, where length contraction also begins to play a little part here, and we're just going to start off these wires with having the same amount of charge, no net electrostatic charge, before we run current through them. And then, in order to run current through them in the same direction, why don't we just get these electrons moving in the same direction? And this will tell us that we would expect a certain amount of length contraction in these electrons. And now, let's just consider the positive nuclei that are still in this wire, because we don't want to necessarily consider the other relativistic phenomena that will be in play with moving electrons. So we're going to ignore the fact that these wires look net positive, and both of them look net positive, and it looks like they're going to repel. We're just going to focus on what this other wire looks like to these positive nuclei, because we have to realize that for these moving electrons, other relativistic phenomena are at play. So if you look at this, these positive nuclei see a net negative on this other wire, which is immediately going to cause an attractive force. And now, when we look at the electron frame, so we assign the motion to these positive charges, the positive nuclei, we see the same thing, which is why Ampere noted his observations that you indeed see an attractive force between currents that are running parallel. Oh, also, I don't know if I mentioned this earlier, but parallel, anti-parallel, just a me kind of thing. Not actually convention, as far as I'm aware. But now, if we're going to run current anti-parallel, that means that these electrons are still going to look length contracted in our regular lab frame, so it looks like it might be the same scenario. But now, why don't we assign all motion, and why don't we take the motion away from these electrons? So we're going to make it look like these are going doubly fast, that these positive nuclei are also going, which means that we uncontract the length of these electrons, we contract the length of the positives, and we supercontract these electron lengths. Which means that these electrons now look in the other wire, and they see a net negative. And if you think about it, we never specified which of these wires it was. So these electrons in the other wire, when you go to their reference frame, when you go to their hometown, they experience the same thing, which is why we see this net repulsion between the two wires that Ampere noted. So, as a result, length contraction and time dilation are both to explain why we know magnetic phenomena, or at least how we currently understand them under modern physics. And thank you for watching and holding in there. And next time, we're going to dive in a little bit more into Lorentz forces, I think, and start talking about more practical applications of mechanics of magnetism.